let's get started. Good morning, ladies and gentlemen. I'm Hiro Yamazaki from University of Cambridge. And today I'd like to talk about some 2D and 3D results from my CATSA model over complex topography. And because we are in the vertical session at the moment, my model also has a characteristic in vertical coordinate. And first I use CATSA for topographic representation. And also I use a block-structured Cartesian mesh refinement in vertical grid. Here the background topography is a map of topography around my home university, Kyoto. And topography, in Kyoto in the city center is pretty flat, but our city is surrounded by complex mountains. And although this map uses 250 meter square mesh, this is currently high resolution in atmospheric models. Using a super computers, we could have less than 100 meter resolution in the near future. And as Ian Lee mentioned at the beginning of this session, the commonly used terrain following coordinates have some problems in simulation over steep topography. And because if you increase the horizontal resolution, there should be a lot of complicated slopes and steep slopes. So that's why another representation of topography, for example, cast cells, would be required in future high-resolution models. So my model, named Sayaka, aims at such kind of outer high-resolution simulations that use horizontal grid intervals of less than 100 meters over steep mountains. Here's the description of my model. And the name of Sayaka doesn't have particular meaning, basically just a popular Japanese girl's name. And one of the difficulty in CATSA modeling is develop a 3D model is much complicated than 2D model. So basically the biggest aim of this talk today is show how my model works in 3D through some preliminary 3D results. And my model is currently just a regional and dry model. So I introduced only subgrid turbulence parameterization for physics process. And the equations are fully compressible. And we use finite volume method for spatial discretization. And these three blue-colored figures are the characteristics of my model. And though I don't discuss about this original semi-staggered variable arrangement today, but there's a really good video 3 weeks ago. I gave a talk in this institute, and a video is available on the Newton Institute web seminars. So please have a look if you would have interest. And in addition to this variable arrangement, again, my model has two particular characteristics. One is CATSA, and second is a block-structured mesh refinement. So now I'm going to explain the details of these characteristics of a model and show you some results afterwards. All right. So again, first, the most distinctive feature of my model is the use of CAT cells as a representation method of topography. And it's generally accepted that one of the greatest concerns in CATSA modeling is how to avoid impractically strict CFL condition due to the small CAT cells. Here I have listed some of the approaches that have been proposed to avoid this small cell problem. And so far, basically all these approaches gave good results, but each method has certain advantages and disadvantages, especially has different levels of complexity and also different levels of accuracy and so on. And in this study, we use relatively old-fashioned and really simple cell merging approach to solve this problem. The concept of this method is really simple. We just combine the small cells to neighbor cell to avoid the really strict CFL condition. And we use both vertical and horizontal combinations depending on slope angles. Here, small cells on gentle slopes are combined vertically, and small cells on steep slopes are combined horizontally, either left or right in the fluid. This approach has the advantage of naturally avoiding severe CFL restrictions, maintaining the rigid evaluation of cell volumes, and also keeps the model's conservation characteristics. Here's a 2D example of the simulations of flow over steep topography using a terrain-flowing model developed by Asut-Muller in 1989, and also my Cartesian model using cell merging. In this test, a semicircular mountain is represented in a relatively coarse resolution. And we can see that in the terrain-flowing model, the computational grids are largely distorted at the foot of the mountain due to the steep slopes. On the other hand, the Cartesian model keeps the model levels horizontal and merge the small cells to neighbor cells either vertically or horizontally. This is the result of flow after 60 minutes of integration. The right picture shows the vertical velocity field calculated by the terrain-flowing model, and the left picture shows that by the Cartesian model. As you can see, the Cartesian model successfully reproduces smooth wave propagation, and the result is clearly less noisy than that of the terrain-flowing model. Especially Schupier's vertical velocity mode appears just above the mountain, disappear in the Cartesian model. Therefore, this test simply proves the advantage of Cartesians over the traditional terrain-flowing grids for simulating flow over steep topography. Now, in addition to the small cell problem, there's another problem when you introduce Cartesians to atmospheric models. That is how to obtain high vertical near-ground resolution. As you know, in order to resolve the boundary layer around the topography, model levels are commonly spaced more closely near the topography. And in the terrain-flowing models, this is accomplished by easily with vertical stretching grid. However, in the Cartesian model, high near-ground resolution is more difficult to obtain, in particular when there is a 3,000 or 4,000 meter high mountain. And if you actually have, say, 10 meters vertical resolution near the ground, the number of levels it requires can be quite substantial. So we need some method like this red line to achieve very high resolution only near the topography. So to cope with this problem, my model Sayaka employs a block structured Cartesian mesh approach in combination with Cartesians near the boundary. In a block structured mesh refinement, our flow field is divided into a number of blocks like this, and each block has the same number of cells. This is the most distinctive characteristic of this mesh refinement approach. And while Christian Jablonski uses same type of mesh refinement on the sphere, on the horizontal mesh on the sphere, we use the same concept of mesh refinement vertically like this. For example, to obtain locally refined block structured mesh around this topography, first we divide the domain into a coarse Cartesian mesh. Then divide the blocks that cross the topography into 4 blocks in 2D case and 8 blocks in 3D case, like oak tree method. And repeat this process again and again until you get as high resolution as you want near the topography. Next, adjust the size differences among blocks to guarantee a uniform 2:1 mesh resolution at the fine coarse block boundary. And then remove the blocks that are located completely inside the topography to avoid the unnecessary calculation inside the topography. Finally, build a Cartesian mesh of equal spacing and equal number of cells in each cube. For example, in this case, there are 4 different sizes of blocks, but I put 8 times 8 cells in all the blocks, regardless of the size of the blocks. Therefore, the local computational resolution is determined by the size of the block, so that locally defined grids at arbitrary boundaries is obtained in the same process. So one of the attractive features of this block structured mesh refinement is that uniform Cartesian mesh in each block allows the direct use of any existing Cartesian grid code. And moreover, the same number of cells in each block provides an advantage for parallel computing because the load balance of each block should be equivalent. So now, in applying block structured mesh refinement to atmospheric models, flux matching between different sizes of blocks is imperative to ensure the mass conservation in entire domain. In this study, we proposed a simple flux matching algorithm, which is suitable for block structured Cartesian mesh refinement. Here we use a sub-cycling time step. I mean, the coarse cells uses twice larger time step than fine cells. So here we ensure that coarse cell flux, here Fc, is equal to fine cell fluxes Fl and Fb accumulated during the sub-cycling time steps, and matches the flux using this simple calculation. This algorithm is really simple and doesn't make a big overhead, but ensures the mass conservation to the machine precision. I will demonstrate it numerically from the next slide. So in this test, I integrated a simple heat diffusion equations on a refined mesh to examine the ability of the block structured mesh approach. Here the domain consists of 112 blocks with 64 by 64 cells in each block, and zero gradient conditions are imposed on the boundaries. And first, as the initial condition, I heat the middle domain and calculate the heat conduction process. These figures show the simulated temperature field after 100 hours of integration. And the left picture uses the flux matching algorithm, and the right picture doesn't use a flux matching. Though both results give smooth conduction of heat, the simulated amplitude in the without flux matching case is much smaller than with flux matching case. So to make it clear, I show the time change of the mean temperature normalized by that in the initial state. It clearly shows that with the flux matching, the mean temperature remains constant, while it decreases to less than 85% of the initial value after 100 hours of integration without flux matching. And this picture shows the speed-up ratio to estimate the scalability. Here I use OpenMP to parallelize the model code. And the power efficiency is about 80% at 8 processes, both result with and without flux matching. This indicates that the matching algorithm doesn't alter the power efficiency of the block-structured Cartesian mesh approach. And though the current parallelization efficiency is not really super high, but the code has a room for improvement. So it's promising, I think. So finally, I'd like to introduce some mountain web tests using 2D case first. In this test, the domain is divided into these blocks, and I used 4 sizes and different blocks, and each block has a 20 by 20 cells. Different from the last test, this one is a XZ domain, and I put the horizontal initial constant horizontal velocity from this way, and there is a semicircular mountain located on the boundary. And the left picture is an enlarged, right picture is an enlarged view of the block contains the topography on this block. And the block has 20 by 20 times cell. And the semicircular mountain is represented by car cells with cell merging. Yep. So this is a flow result on the locally refined mesh, and the result is compared to the uniformly refined mesh as a proxy of the exact solution. As you can see, the model successfully reproduced a smooth and accurate mountain wave comparable to the uniform fine-grid computation. Now the final result I show you today demonstrates the performance of the model in 3D. In this case, the domain is divided into 3 layers of the blocks. And here each block has 12 times 12 cells, and the 3D bell-shaped topography is located on the center of the bottom surface. And I used the same topography as used in Sarah Jane's 3D cluster paper. Now here's the flow result for the vertical velocity field after 30 minutes of integration. The left picture shows the vertical XZ slice through the center of the hill. We can see the wave propagation similar to the 2D case. And in the right picture is a vertical XYZ slice 2 kilometers downstream of the hill, about this line. And this shows the result is actually in 3D and symmetric about the hill. And this picture are the horizontal slices of the vertical velocity field for 2 different heights. And this also shows the smooth distribution of the flow field. And we can see a particular U-shaped as agreed well with the analytical calculation. So these results demonstrate that the model successfully reproduces a flow field over 3D topography. Although this calculation uses only the vertical combination, so here's a summary of my talk, and there is a characteristic of my model. And the next step is using a horizontal merging, implement a horizontal merging into my model, and actually see the 3D result over the steep topography. Thank you.
I have a comment on the block structured refinement. So what you obtain is that you somehow, if you are interested in a LES simulation near mountains, that's of course the thing which is necessary. But as you mentioned, if you just wanted to have appropriate resolution for the physics routine, that means you want just an ordinary weather prediction or climate model, we said, There's a simpler method to achieve that, and that method is implemented in the NASA climate model. The NASA model is not a cut cell model. It's an ETA model, which is not so good as a cut cell model, but this idea can be transferred and has been transferred to the cut cells. And the idea consists of computing the physics routine on a finer mesh independently, and they are a little bit connected. So that's a simpler way if your aim is just to introduce your cut cell into an ordinary weather prediction model. For that purpose, this block structured refinement would be rather expensive. It's more a thing for a research model, I think.
Okay, thank you.
In your first picture where you showed a comparison of gravity waves over a mountain, they seem to have a different wavelengths. Which one is right? Now the very first one, like if you go back in your slides to the beginning,
I think the 2D
there was a comparison. Sambo Euro 1989, no, earlier.
slide 3 or 4.
3 or 4. Are this?
The first mountain wave, the very first.
Ah, okay. This one?
Sorry, the question is?
The momentum
The
flux.
question is, they appear to show different wavelengths.
Yes. So the amplitude is much smaller than this one, you mean? Or
Now the wavelengths, like the
wavelength?
if you look the contour line, the solid contour line in the top right corner,
Top right corner.
they are much more. If it's at the same time, the picture, the
Yeah.
waves should be at the same spatial location.
Yes, so in this paper I examined in detail about this result. I mean, at first amplitude is quite different and wavelength is also a bit different. So I compared the result with orthogonal coordinate model as a proxy of resolution, and I confirmed that my model has a reasonably accurate result. So the biggest difference between this one and this one is I'm using a merging cells. So basically the resolution near the boundary is twice larger, twice lower than this one. So this is a simple comparison, but there's a lot of difference. So we couldn't expect the same result with this case. Is it explaining your question? So
Do you have a high resolution simulations or converged so that you can look at that phase structure that's higher up to see which one is closer to
yes.
the converged solution?
So I got a higher resolution one of my model and also an orthogonal grid model. So yeah, I will look up later in detail. I checked it out in the paper, and I'm sure it's fine.
The other thing we're looking at is that if you, on the momentum flux profile, is that the next slide? There's a very sharp drop-off of the momentum flux from dimensionals 1 to 0 in a very small distance. And so there must be a very strong onset to the absorbing layer. And that could produce some partial reflections. So that's something else that
Yes.
often the design of the absorbing layer unfortunately has effects on embittered region below.
Yeah, so I experienced some difficulty to examine this result is accurate enough. First, the problem is if I put the large damping layer on the top, it's quite difficult to observe the everything properly. So I can't calculate after 60 minutes basically. So it's quite difficult to obtain the result in sufficiently, how can I say, causally.
So you mean after 60 minutes, there's
there's
reflections that are coming back?
Yes. So I can't get the result in a very long time calculation. You know what I mean? I'm sorry. Yes.
Do you have an estimate of which order your method is, especially for the cut cells?
Order of accuracy.
Yeah.
Yes, I have some. So in the uniform mesh refinement, my cut cell uses a bit of first order approximation in boundary, but I confirmed that the model has a globally second order. So I would say the order of accuracy is nearly second order, but in between first order and second order.
In which norm? In which norm did you measure it?
So a custom method and
No. In which norm did you measure that?
no L1, L2, and L infinite.
Okay.
Could it just leave on that slide? Could it possible the difference between the two solutions we are talking about? If you look at the current following, no, just this one. Yeah, no, the green. Yeah, that's the slide you just showed. No.
Sorry, which one?
Yeah, the
The cut cell
previous
grid.
one.
The cut cell.
The
The
next
cut
one.
cell and non cut
Next
cell.
slide.
Page 7.
That's 7, yes.
Oh no.
No. Only that one. Okay, yeah. Could it possible because the mountain wave propagate perpendicular to the surface? So from this perspective, current following coordinate seems catch better the mountain wave propagation than the cut cell is actually you split that a vertical component into two, horizontal and vertical. So I'm wondering whether this will have an effect on the mountain wave.
Sorry, I couldn't understand the last of the.
Right, because the mountain wave,
Yes.
when you have wind impinging on the mountain wave going this way, which actually perpendicular to the mountain. Now you separate that. In the current following, it's actually quite accommodated with this mountain wave direction. But in the cut cell, you actually separate all into X and Y. Everything is the component of X and Y. You try to use an X and Y component to construct the mountain wave component, which is probably in your corner. I guess that's just wondering. I'm wondering whether that's a possible effect.
So, something is separated.
Well, I think one thing he's saying is that for the mountain wave,
Yeah.
at low levels right near the mountain, the theta surfaces correspond pretty closely to the terrain following coordinate surfaces. And so that you get some benefit from that. And he's wondering what the trade-offs are between that, which might be a benefit, and the cut cell approach where you
Yeah, just think
don't
about
have
the
the, like,
wave
horizontal pressure
direction.
in there.
Thinking about the wave direction, and you agree relative to wave direction. That's all I'm saying.
So it's going to be a pressure gradient problem, right? So in a model, pressure gradient doesn't have an approximation, and every pressure gradient calculated precisely. So I don't think there's a serious problem, but probably I have to really explain about what's going on in the Cartesian model too.
Yeah, it's not so much an issue of a problem, I think it's just a trade-off of
Yeah,
of
there
accuracy.
should be a.
But I
Yes.
think for the steeper mountain, then the cut cells was producing a lot less kind of disturbance or distortion right near the terrain.
And this test case is really extreme test case. I mean, the grid is really distorted to make the comparison clear. But basically, we shouldn't use this coarse grid for this mountain, I think.
Well, I think our time is about up for the session, so we thank you again and all of you.